During this module, we will explore hypothesis and significance testing. By the end of this module, you'll be able to construct hypothesis tests and analyze significance of results. Let's first consider an example. A bearing manufacturer historically can fabricate bearings to a 2.00 millimeter diameter with a standard deviation of 0.061 millimeters. They know this from years of experience. But still, quality assurance engineers regularly sample boxes ready for shipment to ensure quality. On one such test, 25 sampled bearing measurements indicate an average diameter of 2.03 millimeters. Does this quality assurance test support the hypothesis that the true mean bearing size of the whole box is still 2.00 millimeters? Can this be said with a 95% confidence level or a 5% level of significance? The word hypothesis in the previous example should have us thinking about the scientific method. Principles of the scientific method are useful in empirically acquiring knowledge from observation or decision making. The general steps in the scientific method that are iterative include observation, establishing a question, researching a topic area, forming a hypothesis, such as the bearing diameter, testing that hypothesis with an experiment, such as a sample, analyzing data, and reporting conclusions. Now, this formal scientific method is less common in industry, but still, decisions rely on scientific principles. We just don't have the time to do science fair projects in industry. But we still want to have scientific conclusions. So scientific refers to a hypothesized conclusion that can be testable, typically with measurement-based statistical tests. So what is a hypothesis? A hypothesis is a statement that something is believed to be true. A hypothesis essentially is a proposed explanation or a conjecture of a phenomenon. As stated before, a scientific hypothesis must be testable, meaning that there must be some clear criteria for evaluating a test. A hypothesis should also be falsifiable, meaning that a conclusion conflicting with the expected outcome could be possible. Hypothesis testing uses tools of statistics as the core of the scientific method for drawing conclusions, with a null hypothesis H0, such that the difference between some measured value of a population and an assumed behavior is small enough to be considered as due to random variations alone, and often with an alternative hypothesis H sub A, such that the difference between observations and expected behavior results from something other than random variation, such as systematic effects or a cause. Hypothesis tests generally evaluate whether measured differences in values between sample data sets arise from normal variations alone, or whether something has changed between the data sets. If the sample data are inconsistent with the null hypothesis, we, quote, reject it in favor of the alternative hypothesis. Otherwise, we do not reject the null hypothesis. This language is intentionally distinct from saying that we expect the outcome to be certainly true. Failing to reject generally means that the test has not identified a consequential relationship between some phenomena. In our example, we ask, is a measured sample mean a reasonable approximation for the population mean, comparing information for the observed variation in the data with the assumed population distribution? We express this with a null hypothesis H sub naught colon x prime equals x naught, such that we expect the diameter x prime to be equal to a specific number x naught. Based on historical experience and specifications, we define x naught equal to 2.00 millimeters as the mean population diameter. The alternative hypothesis depends on the exact purpose of the hypothesis test. Since we want to determine if the sample mean x bar differs from the population mean, the alternative hypothesis is expressed simply as x prime not equal to x naught, such that the diameter values are not equal to the specified value x naught. This is called a two-tailed test, such that The alternative hypothesis could be true if either x prime is less than x naught or x prime is greater than x naught. It would be a single-tailed test if interest was in knowing if the alternative hypothesis was x prime greater than x naught, right-tailed, or x prime less than x naught, left-tailed, assuming a normal distribution. For cases when we know or specify the population standard deviation sigma, such as in manufacturing quality control tests, we use the z-test, defining the observed z variable as z equals the mean minus the test value x, divided by the standard deviation sigma divided by square root of n. The z variable is evaluated against critical values of z at a desired level of significance alpha, where the probability of z exactly equals 1 minus alpha. We do not reject the null hypothesis H naught if the values of the test statistic lie within a high probability defined area of acceptance region. We reject the null hypothesis if it occurs in the low probability tails below the significance criteria values. Some common levels of significance alpha are 10%, 5%, and 1%. The t-test is used when the population standard deviation is not known. Instead, we use the sample standard deviation S sub x, with t equal sample mean minus the test value x divided by the sample standard deviation and divided by square root of n. A p-value indicates the probability that the numerical difference between two tested values, such as the critical statistic and the test significance, is due to random chance. It's the observed level of significance. A small p-value indicates that effects other than random chance are influencing variation in the sample. So to calculate the p-value, assume the null hypothesis is true and compute the observed level of significance corresponding to the test statistic. To summarize the hypothesis test method, first we establish the null hypothesis, such as h sub naught, where we call x prime equals x naught. X naught is the population or target value. And then we establish an appropriate alternative hypothesis, h sub a. Next, we assign a level of significance alpha to determine the critical values that set the rejection region. Then we calculate the observed value of the test statistic, and we compare the observed test statistic to the critical values. If the observed statistic is in the rejection region, reject the null hypothesis. Otherwise, do not reject. Next, we introduce the chi-squared distribution. Chi-squared is a PDF, or probability density function, derived from plotting the standard deviation for many data sets, each with n data points or new n-1 degrees of freedom. It represents the distribution of sum of squares of independent standard normal random variables. And that chi-squared can be used to find a confidence interval estimate for the population variance or standard deviation. And the sample variance is usually the best point estimate for the population variance. So for a normal distribution, chi-squared is simply equal to the degrees of freedom times the sample variance divided by the population variance. And we can use a significance test to see how well the sample variance predicts the population variance, where we have probability within a region of chi-squared equal to 1 minus alpha. Here we see a chi-squared data table and a chi-squared plot. In the table, each critical value of chi-squared corresponds to an area given in the top row of the table, and that area represents the cumulative area located to the right of the critical values. The chi-square distribution is not symmetric, so in that way it's unlike the normal or student's t distributions. As the number of degrees of freedom nu increases, the distribution becomes more symmetric. The values of the chi-square can be 0 or positive, but they can never be negative. And the chi-square distribution is different for each number of degrees of freedom, which is the degrees of freedom, df, or nu, is equal to n minus 1. As the number increases, the chi-square distribution approaches the normal distribution. Chi-squared can be used to establish a confidence interval for the population standard deviation or population variance. First, we verify that the required assumptions are satisfied, and then we use the n minus 1 degrees of freedoms with the chi-square table to find the critical values, chi-squared sub r and chi-squared sub l, right and left, that correspond to the desired confidence level. Then we evaluate the upper and lower confidence interval limits using this format of the confidence interval. N minus 1, which is the degrees of freedom, times the sample variance divided by the chi-squared on the right, and then also N minus 1 times the sample variance divided by chi-squared on the left tail. So for the population standard deviation, it's similar. We just take the square root of those numbers to find the limits. In this example, we can find the critical values for chi-squared for the critical regions containing an area of 0.025 in each of the tails of the left and right side of chi-squared. So we'll assume a sample size of 10 and the degrees of freedom of 9. With that, we really have alpha, the significance of 0.05, 5%, which corresponds to alpha over 2 of 0.025, and then 1 minus alpha over 2 of 0.975. So on the left tail, we find in the table on the left that when we have degrees of freedom of 9, chi-squared for 0.975 is 2.70, and on the right, the chi-squared on the right side is 19.0. One-way ANOVA, or analysis of variance, is a statistical method for comparing several population means. A simple random sample is drawn from each population, and the data are used to test the null hypothesis that the population means are equal. A single factor is considered as the cause of variation in the data, among treatment means and within treatments. So to use one-way ANOVA, the following conditions have to be present. The populations of interest must be normally distributed, the samples must be independent of each other, and the population must have the same variance. Results determine whether the variation caused by the factor is sufficiently large multiple of experimental error to reject the null hypothesis. Basically, ANOVA looks at the average variation within all the samples and compares it to the variation between all of the samples. An F statistic is calculated from the ratio of the between variance and the within variance. If F is greater than a critical value, then we know that at least one of the samples is different from the others. Some examples of ANOVA are covered here, and this was also discussed in the pooled mean statistics in the previous module. This concludes the hypothesis and significance testing. During this module, we've constructed several hypothesis tests and used them to analyze the significance of results.